Hello, this is the second day of the CFD short course, and this is lecture 3 on the finite volume method. The basic methodology of finite volume method is that the field of interest is divided into a number of control volumes. Each control volume can be of arbitrary shape, and different volumes can be of different shapes. The only requirement is that the field must be completely filled with these volumes with no vacant space left between them. So mostly we use polygons or polyhedra. For simple geometries, sometimes it's better to use rectangles or quads or triangles or hex for 3D. But in theory, you can use any control volume. Now, the numerical node values are computed at the nodes, and there are two types of nodes. The field nodes, which are located inside the control volume, and then boundary nodes, which are located at the external boundary segments. I find this tank and tube analogy very intuitive. And what we are saying is that imagine that each of the control volumes is an independent tank, and they are in touch with each other. They are in contact with each other. There is no vacant space. And there is a tube connecting each of the tank with its neighboring tank. So what happens is that the tanks are equivalent to the control volumes, and the tubes are equivalent to the grid lines, basically. Each tank has one average value. Okay, the values may vary within the tank, but we represent it by one average value so that when we multiply the average value with, let's say, density and the volume, we get the total mass in the system. The only way for something to leave the tank is to flow out of the tubes to its neighbors. Okay, so fluxes go in from one tank and go out to the other end. So this way, the FVM is inherently conservative. Okay, a flux cannot just leave out of one tank and not go anywhere. It must go into the next tank, or it must go out of the boundary. Okay, so it totally conserves the flux or the mass and things of that nature, whether it's thermal or mass or any other conserved quantity. Now let's look at, to illustrate it further, here is a simple 2D realization of a control volume. And one node is placed inside, which is called the field node, and represents the average value of the tank. Quite often, we place it at the geometric center of the tank, or sometimes where the grid lines cross, but it doesn't have to be. It could be any place. It's just that it should be such that when you multiply it with the total volume and with the value at that node, you should get the total amount in that tank. So these are field nodes. Now, when one of these control volumes touches the external boundary of the equipment, not a tank touching another tank. I'm talking of a tank touching an external boundary, right? At that boundary, the boundary segment, we place one node, and that node we call the boundary node. Okay, what do we do with the boundary nodes? Boundary node is used either to impose the boundary conditions for the problem, such as Dirichlet boundary conditions, or we compute the value at the boundary from the field nodes through an equation, such as for von Neumann value or radiation boundary condition, where we say we know the gradient or the combination of gradient and value, and this is what the value at the boundary should be. So let's look at the methodology. So intuitively, finite volume can be generalized to any arbitrary control volume. So just for illustration, I'm showing you a 8-sided polygon here. Okay, it has 8 surfaces, okay, numbered 1 through 8, okay, and the fluxes flow through these 8 surfaces to 8 tanks which are connected to this tank, if it's inside the tank, okay. So all we have to do is keep track of those fluxes and keep track of value in the tank. So it's just high school bookkeeping. That's what we're going to do. Okay, just give it a different name called CFD. Now the balance equation is given by this equation here, which says that accumulation is net flux inflow plus net generation, right? So what is the accumulation? Accumulation is the average value of the tank, phi average, multiplied by, this should be delta V and delta T, the volume of the tank, the time step that we have, and that's the increase in that's the value at that time, right? Now, what is the flux that is coming in? Flux that is coming in is this one here, okay? It's flux at each component multiplied by delta A at each component multiplied by delta T, right? The area times the flux, okay? G is the average generation within the tank of that property multiplied by volume and time, okay? I've simplified this somewhat to eliminate the normals and all that, assuming that we have normals are at the normal of this, the areas are normal to the connecting lines. So if so, then the flux can be composed of two parts: the convective flux, which is the velocity times the property, and then the diffusive flux, which is gamma k, the diffusivity multiplied by gradient, and we can represent the gradient saying it's the distance between 2 points, one inside the tank and one outside the tank, right? So each surface is connected to two tanks, remember? So these are the values inside and outside the tank, and we going to call this the inside, and the tank connected to it will be outside in this case, okay? This is a simplified version just to give you an idea. Now, let's look at a Cartesian control volume to illustrate, because we're going to use this quite a bit for the next few slides. So here is a 2D representation of a control volume, which is the shaded area, okay? So this is the node inside the tank called P, and on the east, west, north, and south side, we have 4 other tanks which are connected to that, which are not shown. I've just shown the centers of those nodes, right? Okay. So then there are the interface surfaces between the tanks, right? The next tank starts here like that, okay? So the interface on this side is W, small e, small north, small s, and fluxes flow through these surfaces, these are the J's that flow through the surface, okay? So these are flux components, and this basically tells you what the tank is, okay? Now, for 1D, the general transport equation can be simplified to say d phi by dt plus dj by dx, change in flux is equal to s, where j is equal to u phi minus gamma delta x, right? This is the flux that we have to define, right? So the convective plus diffuse is the net flux. Now, let's integrate over this control volume, which is basically saying, let's do the balance of this property for this volume. So the accumulation term is basically d phi by dt, delta t, delta v. So what does that become? That becomes the phi at the new time step minus phi at the old time step multiplied by delta v, right? Okay, because the delta t is eliminated with the dt. Now, this phi, the property, I'm calling it a tilde, right? Because tilde is a representative volume average. As I said, that the actual value of phi may vary in the property, but we are saying that this is the average value, okay? So this is the average value in the tank at the new time step, average value at the old time step, multiplied by the volume. Let's look at now the source term, which is equally simple, that we say integrate the source with time and volume. And we write it like this. Why do you write it like this? Because source itself may be a function of time. We don't know at this stage, okay? If source is a function of time, we can write it as a combination of the source at the new time step and a source at the old time step. Theta is the averaging factor or relaxation factor, or you can, what proportion of the old and the new do we combine? Now, typically, if we are saying, let's assume central differences in time, then theta would be half. We'll take half of the old, half of the new. Now, the second thing is that this tilde means that the S that should go here is the average value over that phi at that time, right? So again, just like the phi itself varies, the source can vary over it, but we are going to deal with the average of that source, okay? It's the volume average value. So theta is a measure of implicitness. If theta is 0, right? So theta 0 means we don't take any new value, we go only to the old value. That means it's an explicit. We are saying, let's use the source at the old time. If we make theta equal to 1, we'll use the source only at the new time. So we'll compute it at the new time step if there is a time dependence. Now we come to the fluxes, which is a more interesting problem. Okay, here I show the flux at two faces, east, J east and J west. These are fluxes are at the face, right? Not at the volume point, at the field nodes, right? Because this is the surface. They're leaving a surface, entering a surface. So the integral of this equation is basically from Gauss theorem, the flux multiplied with the normal component multiplied dA dt, and in this case the normals are normal to this boundary. So to make it simple, so we can say this is J at the east boundary minus J at the west boundary, multiply the area, which is delta y, and multiply by the time, right? Now, what is this flux? This flux is the value of velocity, which is leaving this surface E, right? This is the velocity at the E, which is intermediate to P and big E, right? Multiplied by the value at that point, okay? It's the value at the surface and velocity at the surface. Similarly, the convective flux is the diffusivity at that surface at E, and the gradient that determines that. Now the gradient we can easily write as phi E minus phi P over delta X E, which is the distance between these 2 points, right? So this is the flux and we get that. Now, how do we compute the value at the E point, right? Like we did for the source that was in time, here we can do it for space, and we can say that this value is a combination of this value or this value. That also is a requirement for any smooth or systematic solution, right? So that is needed for other reasons too, we'll see later in one of the talks, okay? So we have to assume that this value must fall between these two values. So therefore we can interpolate it with an interpolation coefficient called alpha E. And so this is phi times the alpha E, right? Phi times this value plus 1 minus phi times this value. So this gives you basically an equation which is written like this: AE phi big E phi P phi E. So now, except for a constant that we have introduced, the value at the boundary is determined from the node values, which we are going to compute. Now, if you rewrite this equation, you will find that this equation can be written as a CE, a influence coefficient, what we call it, multiplied with these two values. Influence coefficient times the difference between phi P and phi E plus the value at the central point multiplied by velocity, right? Okay. Now, what is the influence coefficient here? Influence coefficient, if you see from here, is the diffusivity divided by the distance, and then 1 minus alpha times what we call the Peclet number. Now, what is Peclet number? Peclet number is a measure of the ratio of convective fluxes to the diffusive fluxes, okay? Larger the Peclet number, stronger the convective flow. So Peclet number is basically velocity times delta, the distance, or gamma. Basically, it's gamma over delta XE, UE over gamma over delta X, which delta X goes on the top, right? Okay, so this is the Peclet number. So we see that one physical requirement is that, for example, if we decrease the value of E below P, then flux should go from here to there, right? It should go outside. Similarly, if we decrease the inside value, and this is larger, then the flux should come in, right? Okay, this is a physical requirement of the fluxes, right? So that is very important, okay? So as phi E decreases, the flux JE should increase and vice versa, right? So if when we look at this, we find that that's not always the case. There is a CE multiplying phi p minus phi e. So let's take the gradient of JE with phi e, right? To see what is going on, right? So this shows that the gradient is minus CE. Okay, that means that the gradient of the variation at this point is a minus the coefficient that we computed, right? So since the coefficient was this quantity and we wanted to be negative, you can take this in an exercise today, that what this would imply is that the Peclet number must be less than 1 over L phi e for this to be true, right? You will look at this equation, and basically if you do the math, you'll find that it puts a restriction on PE as how you can interpolate under what condition, and it's a function of PE. This is a very important conclusion for convective flows, convective diffusive flows, and this basically determines how we use the scheme. So the secret of a successful scheme is that the Peclet number must be less than 1 over L phi e, right? The interpolation must be done such a way. Now, if you look at the central difference scheme, it says L phi is half, right? Central difference is basically if this is in the middle, take average of the two values. That seems correct, right? So phi e is phi e plus phi p. If we do that, we'll find that CE is the correct sign only if Peclet number is less than 2. So what that means is that for central finite differences to give you a physically plausible solution, the grid size must be in this ratio. That means if you increase the velocity, the grid size should decrease. Or if you decrease the diffusivity, like in high Reynolds number flows, then again the grid size must decrease, right? Okay. So this is a very important conclusion, and this is the main, what I call the holy grail for CFD. So if we do not do that, if we do not reduce and we use the Peclet number greater than 2, what would happen is that our matrix of equations will no longer be positive definite. That's the mathematical definition, right? Physical definition, I already told you that what it means is that the diffusion is occurring in the wrong direction. That means I am inside a room which is warmer than the outside, and I'm gaining heat from the outside. Well, doesn't make any sense, right? If I'm in a warmer room, I should be losing heat to the outside, okay? So that's the physical explanation, and the mathematical explanation is that the matrix will no longer be positive definite, which is a very important issue for solving the matrix. So various people have come up with various schemes. This is called Upwind. We had discovered it 1965, 66 independently, but then we found that Kura had already discovered it in 1952. So he is the one who was the first person who came up with this. So what it says basically is, look where the wind is coming from. What we're saying is, if let's say the flow is going out of this tank and it's going there, then the value it's carry is most probably this one, right? It may be influenced somewhat by what's happening outside because there's a variation, but the bulk of the value would be here. If I make the speed very high, then I know for sure that this is the value which is being carried out, right? I mean, for example, I'm in California, in LA, and when the deserts around me get very hot, I get wind from there, and those are hot winds. Similarly, if the wind comes from the north, from the cooler parts, from the mountains, it's cold, right? So we should give some credit to that component. So the basic idea of upwind is that if the velocity at this point is positive, flow is going out, then let's say it's carrying the value P, therefore alpha is 0. If, on the other hand, velocity is negative, flow is coming in, then it's bringing the value of E into it, right? So alpha E is 1. So this is the crux of the upwind. One thing we did at Imperial College was to put it in this form. And what this form means is that you don't have to have an if statement, which in our days was very expensive. This is a mathematical expression, which basically says compute it like this. And the east coefficient now can be written in terms of this alpha E in this form. Now UE by PE is positive, this is positive, and U by UE, and we know Peclet number would never exceed, if it exceeds 2, then you'll find that the absolute of all these quantities will basically give you a C, which is always 0, because this quantity is added. Now let's look at another one. What we found over time was, after a year or two, was the Upwind was creating what we call false or numerical diffusions under certain flow conditions. What are those conditions? Typically, if your flow is not aligned with the grid lines, that means it's not leaving your surfaces at a normal angle, then you can't just take the X component or the Y component because the flow is being affected along a streamline, right? So the angle that the flow makes is important, and the speed with which it enters or leaves is also important. So numerical diffusion increases when the angle increases up to about 45 degrees, and then it decreases when you align with the grid, right? So there were a number of solutions we came up with. Spalding had also had a solution which was exponential, but it was very expensive to compute. So I came up with an adaptive refinement called the hybrid scheme. So what this scheme says is that look at point by point. Don't look at the whole, all of them together. Look at each point. If at that point Peclet number is less than 2, then, well, let's use central finite difference. Nothing wrong with it. Let's use alpha equal to half, and we get better accuracy, right? And lower false diffusion. Now, if Peclet number is greater than 2, then use Upwind as we defined, right? So hybrid is more accurate because essentially we don't enforce this Upwind condition unless it is needed. Okay, in the extreme, if of course, in the extreme, if your grid is very coarse, it will become similar to Upwind, right? But in general, for a general flow, you'll find that the Peclet number velocity varies everywhere, distances vary, so the Peclet number varies. So we look at what the Peclet number is. So, and this scheme is also unconditionally stable because the alpha is never exceeds, never is allowed to put in a place where it will create a negative CE. So there is less numerical diffusion. So this is the scheme which became the scheme that is, and there are various versions of it, okay? Of course, this was not the end of it. And there were many attempts, and there are still many attempts, and there will be many attempts to try to find the Holy Grail. Now, one of those is to use, how about using a second Upwind difference? Now, second order Upwind difference means that you don't just look at the point upstream, you look at another point upstream, you look at the upstream and the gradient at that point, right? So basically we're saying phi E is phi P plus the gradient multiplied by the distance. So this would be on the order of alpha r. So this is basically what we're saying is we say, well, go 1 point up because d phi dr would be computed. So even the point on the west side will come to the picture. So there'll be phi P, phi E, and phi big E and phi big W that will enter because of the gradient conditions here. So the dropping the quadratic term, we get this thing, and then the Upwind scheme. It is second order accurate now, but it can be quite diffusive in some circumstances. There is a convection boundedness criteria which tells you how we can derive a good scheme, okay? So when interpolating the cell center values, we require that the interface value, as I stated before, should be bounded between the cell center values. That's the condition of smoothness, right? So it prevents unphysical solutions provided the interpolated value stays within the values which surround it, okay? So basically we are saying that the value at the face, this face, should stay between those two values when you compute it, right? So this is the convection boundedness criteria. You see some of the high order schemes will not show that, like Upwind differences would put a gradient of this and this in there. So we will not know if this is between these 2 points. It may be different depending on the value of the W point. So if this condition is satisfied at every cell, there'll be no unphysical oscillations, right? So this criteria we can express in terms of a normalized variable. If phi is a value at any point, we take the phi on the upstream side, phi on the downstream side, we divide this difference. So the value must stay between these two. The cell value should never exceed phi delta. So what it means is that at phi C, we must have value between 0 and 1. for the CV. This is called the convection boundedness criteria, and that is that the normal value at the boundedness must be between 0 and 1. Now, this is what we call a normalized variable diagram. And in this one, what happens is that a convection scheme can be shown as a plot of normalized value at cell center versus the normalized value at the interface. So this, I should give a credit here. Credit is to Delgado here, who did this scheme. It's this got displaced, it should have been here. So Delgado could produce this curve, and he said, well, let's plot the normalized variables, okay, in this scheme, right? So it plots the phi C at the center point versus the phi F at the face, right? So C is the center value, F is the interface, and D is its neighbor. So what we do once we get that is that the CBC schemes are the only ones which stay within the shaded region. Any scheme that goes outside will not be unconditionally stable or unconditionally lead to a positive definite matrix. If you look at this, you'll find that only CDS is the one, Upwind difference scheme is the only one so far that people have found, which stays within this triangle at one boundary interval. Every other scheme that has been tried, and there are a number of them here listed, central difference, Quick, LUDS, all these schemes, and there are a bunch of others, they all would fall in this kind of criteria where there is a conditional where they fall, and then there is a part where they don't fall. So you have to stick to those ones. All other schemes go outside the shaded region. Now, there is something called a total variation diminishing, which is also very popular, talking about a scheme. So this was another method to get rid of the spurious oscillations. So we saw from the previous scheme, the NVD scheme, that all other than wind, upwind, all schemes fall outside the CP. Okay, but the problem is that upwind, we know, is only first order accurate, which is not important for very high speed supersonic flows, but it is very important for low speed flows and for, when convection does not fully dominate. So there are many variations of TVD schemes. I'm not going to get into those, and there's plenty of them in the literature, but these address spurious oscillation. So people have come up with all kinds of schemes to do that. Okay, so what is the TVD scheme? TVD scheme basically a scheme which has the following property. It's that it assures that if phi increases monotonically between two cell centers, the scheme should not create a higher value between them. So it truncates the higher values between them and would limit the value to fall within them. So the total variation is defined as the total variation is you look at the point and its neighbor, and you take an average of all those values, and that's the total variation in the field, right? Okay. Now this scheme is said to be TVD, total variation diminishing, if computed value at the next iteration or next time step is less than or equal to the previous value at the previous time step. Okay. So total variation at next step, time, or in iteration should be less than the total variation of step n. If so, the errors would decrease with time and the scheme would converge. Now, let's look at the TVD schemes. So the interface value in TVD scheme is written as phi E, phi P plus some gradient, just like we did in the second order upwind, of phi E minus phi P. It's not a gradient, it's called a flux limiter. I'm going to call it a flux limiter. There's different ways to compute it, okay? The flux limiter, it's called. So now let's define a quantity called R. What is R? R is the difference phi P minus the west side, phi E minus the phi P. This is the variation between the points on the two sides of the left side on the right side, okay? So that's the R component, okay? So TVD schemes are those where psi versus R curve lies within the shaded region, right? Okay, so psi is how the schemes differ in computing. So various TVD schemes have different psis, and those psis differ and how they define. So upward scheme is TVD. It stays somewhere down here, I believe, right? Okay, this is the upwind scheme, right? So it has psi is basically 0 in upwind scheme, because for the speed we're going to put it equal to phi P, so psi is taken to be 0, right? Now For the central difference scheme, we are going to take it to be half. So what is the central difference scheme is here. So here it is equal to 1. So this is 1 means it's average. If you put psi equal to 1, you'll get half times this plus this. So that's our scheme. And you see this is where the problem is. It's no longer in the shaded region. Now, quick scheme does something like that. Quick scheme essentially gives psi of 3 plus r over 4. R is the gradient, and that takes you out of it. So quick is quite unrealistic, very fast as r increases as the gradient, the two side increases. There are schemes such as LUD, okay, which is here, okay. So any scheme you get, you can plot. Now, one interesting fact that Swaby, who did this plot, said is second order scheme is one where the flux limiter must pass through 1, 1. Okay, this is the point it must pass through to be a flux, to be a second order scheme. All other schemes are not truly second order, so it doesn't matter what people claim. So this is where the crux of the matter is. You can see there is no ideal scheme, and this is basically tells you some of the best schemes which there are. So let's try to wrap up discretization. Well, believe me, there are many other schemes, but the basic situation is there is no perfect scheme yet. So this is where young research like you can make your mark, put your brain cells to work, and come up with something which would be ideal. Now, what is ideal? Ideal would be that it should be at least second order accurate in space, right? If we want a first order, we already have a scheme. It's a upwind differencing. That's not what we want, okay? It must be unconditionally positive definite. CE must be greater than 0, right? So whatever you use for psi or for intermediate alpha, that must be 0. It must preserve the extrema of the neighbors under all conditions. It must lie, the computed value must lie between phi p and phi e, and so must the cell value between its neighbor. And lastly, it must preserve the total flux crossing a surface, whether that flux is that of mass or momentum or thermal energy or mass component, it must preserve. And that means that the same flux looking from both sides. Look at any surface, flux must be same. If you can get a scheme with these ones, I believe you deserve the equivalent of the Nobel Prize in computational fluid dynamics. Now, all these schemes would eventually give you an algebraic analog, and that algebraic analog would look like this. It'll be AK, some coefficient, influence coefficient, multiply the value at the new time, which is made up of the coefficient of the old time plus S. So this is how it looks like, and K represents over all elements connected to the current element. And if you do this, for example, in our case, we are this 2D stencil, we'll get something like this, 4 components this side, which are the values at these points, connecting the value at this point with their own influence coefficients, plus its source term, which represents. So this matrix can be put in the form, I've not put it in that form, but you can put it in the form Aijx equal to B. You just have to move these terms to the left side. And Aij are the influence coefficients, CAE, and X are the values at the nodes. And B then, what comes in the B is basically S is the stiffness or the forcing function, right? So we'll discuss the solution of this later in this course, but let's now move to some numerical basic facts which make our life very interesting. These are the issues of order, accuracy, consistency, and stability. So let's first look at the order. What's an order of a scheme? A numerical solution on computational grid represents a continuous Euclidean space by a discontinuous discrete space. Here is the continuous Euclidean space. Here is what we know. We only know the value at these points, 6 points, 7 points. We don't know what's going on between these points, right? Supposing this curve had a quiggle here, a very sharp quiggle, which was less than the space between them, we'll never capture it. We'll lose it, right? So we know the values only at discrete points. So we are not in Euclidean space anymore. Okay, this is a very special kind of space. So the values are missing. At the missing point, we can compute the value here by saying it's linear between these two or quadratic between these two. We can do that. But what if this value was not quadratic? What if there was a very sharp point here, right? So we don't know what is going on at these points, and this is what the interesting difference between the two is. So never think of a discrete space solution as accurately representing. That's why people refine the grids and go to smaller grids to find they haven't missed anything, okay? So if there were extrema between coupled computed points, we'll miss that. So the rule of thumb is that to resolve a sine wave, let's say, you must have at least 10 points, okay? Try resolving a sine wave with 3 points. We happen to be wrong, you just catch 0, right? Okay, so if you just have 5 points, you'll catch a delta curve, right? So basically, you have to have enough points that it looks like a sine wave. Now, we know that the form of the derivative that we have is we started with delta f by delta x, and we said delta x goes to 0. Remember that Gauss theorem? And we said when that happens, this becomes the gradient at the point, right? So finite difference method, we're going to use this reverse. Okay, we're going to say df by dx is df by delta f by delta x. Okay, well, that's not fully true, right? Because we haven't gone to the limit of delta x of 0. We removed that limit, and our delta x is very much finite. We can't afford 0x, right? So they are not necessarily equivalent. There is a difference between the two, or they can be different between the two. So delta x can be small, but still a finite value always. So to consider this process, let's take a simple grid of n points, right? So here are n points on a grid, right? F1, F2, F3, etc. So let's see, we discussed 3 kind of schemes that can be used. There is the forward scheme, right, which says basically look at the point ahead, subtract the point where you're standing, and divide by the distance, and you get the forward difference. The backward difference is when you say, look behind you, this is the value where I'm standing, and this is the value where it came from, so I'm behind me, so I'm going to take that value as defining it. Now, what the central difference is? Central difference is, hey, I'm standing here, I have values on both sides, let's take the mean. Okay, that's what that one is, right? So this scheme, whatever we choose, will affect the order, accuracy, consistency, and stability of scheme. We already saw that Upwind is one of these schemes. We use either a forward or backward speed depending on the speed of flow, right? And we know it's stable, but it doesn't, it's first order and doesn't have accuracy. Similarly, we know the central difference scheme is good, it's second order, but it doesn't have stability all the time. So the order of accuracy is that we take the discrete value must approach the exact value in some fashion, okay? So the order of the scheme shows how fast and in what manner they approach that ideal. Basically, the power of delta x with which they approach the solution, right? So let's define error as the value computed minus the real value, right? Fi is the value computed, Fx the real value. So we want that error to go to 0 as delta x goes to 0, right? Okay, so if we expand Fi in Taylor series, we get this one with the backward scheme, this is the saying Fi plus 1 at the point ahead of you is equal to Fx plus delta x, right? Okay, now let's take the difference of this. So if we take the difference of this, we find that we get Fi plus 1 minus Fi over delta x plus terms on the order of delta x, right? And basically delta x by 2 times the second gradient. So if the second gradient is 0 or the higher gradients are all 0, for second, third, fourth, fifth, so on, there is no error, right? Because we resolved it to the delta x error, there's no error. But that doesn't happen in real life. You seldom get that. Only means in a linear function if second gradient is 0, right? So except for linear function, this obviously is not correct, okay? So the error of representing the exact solution by this approximation is on the order delta x. And so same can be shown for the backward differences. So this is called the truncation error. This is error due to truncating the Taylor series from the higher order terms. That's why it's truncation error. So these schemes are of the first order because the leading error component is on the order of delta x. So that's continuous. And that, of course, is only true if the function fx is well behaved, continuous, differentiable, and well-behaved derivatives. Okay. Now, I must say here that the order analysis is very useful, but it can be very misleading for high-speed flows with shocks, other flows with discontinuities such as contact surfaces. And actually, it can be shown that if diffusion was completely absent and only convection was present, then the best scheme actually would be an upwind scheme. Now let's look at the central differencing. Now, if you look at the central differences, that will be given by point ahead and point behind. We expand point ahead and point behind into the Taylor series, and we take the df by dx, will basically get this quantity, right? Okay, here we see that the leading term is on the order of delta x squared. So this is a second order scheme. Now let's look at the order of accuracy. The truncation error is of the order delta x, so it decreases quadratically as delta x decreases. So it's a second order scheme. And similarly, we can show that if we do the second derivative, the d2f by dx squared with central difference, that also would have a second order. So therefore it's a good scheme. Okay, the errors will decrease fast. Now let's look at the consistency. Okay, consistency is defined in a different, I'll come to that in a minute. So here are the 3 points, which gives you the 3 neighbors at the old time step, and we want to compute the new time step, right? So consistency means that discretized equation would reduce to the differential equation when delta x goes to 0 and delta t goes to 0. It's consistent with the physics, right? The difference equation will become differential equation if you do so. Well, it seems it's obvious, but that doesn't always happen. So consider this equation, for example, right? df by dt, very simple equation, a is greater than 0 and positive. So if you use forward differences in time and central in space, and you get this scheme for them, right? There's a by 2 delta x times that, right? So if we do the difference with the discrete term and we subtract from it the differential equation, the differences are on the order delta 2 by 2 plus delta x squared by 6 plus blah, 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 right? So as delta x is reduced, delta t is reduced, well, the RHS goes to 0, so the scheme is consistent. Now, one scheme, there are many that are not, you must check what you're using if it's not a usual scheme. Then let's look at this equation, right? There was a very good and very central difference in time and central difference in space scheme that Dufort-Frankel came up with. It's a very good scheme and still used, right? But it has a typical problem, that a constraint that you must adhere to. So if you do the Dufort-Frankel scheme plus gradient, this is what the scheme looks like. It so happens, if to subtract the actual equation from this and expand in Taylor series, you will get a term on the order of delta t by delta x squared. Okay. Now that happens because this should have been 2fi at n point, right? But we replace the 2fi at n point with a fi at n plus 1, fi at n minus 1. This makes it second order time accurate, but introduces the error on the order delta t. That means that as the grade is reduced, the time step must be reduced faster to ensure a good condition, right? You can't reduce them in a manner where delta t by delta x increases. So that's the constraint. So let's look at stability. Stability basically says the scheme is stable if it does not permit errors to grow unbounded as the solution progresses from one computational step to the next. The difference between the discrete solution and the exact solution must stay finite. Okay, so let's consider this equation. Okay, df by dx plus f again is greater than equal to 0. The exact solution is basically exponent of minus ax. Very simple. Now, if you take this equation and we apply explicit Euler forward differences, then you'll find that the error is exponents of minus a xn, which is a solution at that point, minus a term which is 1 minus a delta x xn by delta x. In other words, a positive power xn is positive, delta x positive, right? Okay. So the solution does not grow only if 1 minus a delta x is less than 1, right? Which means that error would grow if delta x is greater than 2 by a. And so we must have a small grid scheme. So this condition scheme is not unconditionally stable. Now let's use the backward differences. The backward differences, if we use, we find that the error is in this form. Fn is 1 over A plus 1 over A plus, not 1 minus A delta X, 1 over 1 plus A delta X. This is always positive. A is positive. So backward difference scheme, implicit Euler scheme is always positive, always is stable. Central difference scheme, on the other hand, can be shown is always unstable, right? That's very interesting. It's very accurate, but it's not stable for this particular equation, right? So, you know, the second order scheme is less stable than the first order scheme. Yeah. So let's say that we inhabit fluids and fluids inhabit us. It's been a profession for me 55 years now, and I've enjoyed every minute of it. Nothing more could be very challenging. I find CFD to be fun. So thank you very much. And I'm open to any questions you may have. Thanks a lot. And we'll go from there.